All right, welcome everybody to Advent of Code 2022 Day 2. And I'm going to be fully honest, this is actually take 2 of this video because I managed to record an entire version of this with my microphone turned off. Yeah, so anyway, if I'm a little bit lower energy today than I was yesterday, that's why, because I'm actually a little bit annoyed about that. But anyway, let's go on. Thanks everyone for watching yesterday's video. Thanks for all the likes and subscribes and all the wonderful comments about the excellent kimchi over here. So what I learned from yesterday was pretty much everyone likes my cat more than me, which can't really blame them. The cat's fantastic. So yeah, she was equally as much help with today's problem as she was with yesterday's. But anyway, let's jump into today. So today, day 2, we are playing rock, paper, scissors. So this game, the elves have decided that they are, basically they want to sleep closest to the snack pile from the last, the last day, and yeah, they're to determine who gets to sleep closest. They've decided to have an epic tournament of rock, paper, scissors, to decide who gets to sleep closest. So one of the elves comes up to you and he says that he has the ultimate strategy for you to win this game, because he wants you to win because you did really well yesterday and you helped everyone out. So basically your input is this 2-letter sequence which defines a set of results, inputs and outputs for a game of rock, paper, scissors. So basically he tells you this, and then halfway through explaining what it actually means, he gets pulled away to do something else, so you're sort of left assuming what this fully means. But essentially the first column is your opponent's plays in a game of rock, paper, scissors. So A is rock, B is paper, C is scissors, and then X, Y, Z, they're out of order here in the input, but X, Y, Z are then your responses to those plays, and equally they mean the same thing in context. So X is rock, paper, scissors, Y, Z, you get it. So with that in mind, then what your task is to do is to try and compute a score based off this big list of inputs of games. So each row is an individual game, and yeah, you have to try and figure out what your total score is for this. So there's an algorithm here, or a procedure here, that they describe to compute your score. Basically your score is based on the hand that you actually play, so rock, paper, or scissors, and then you also get added to that the fact that either you won, lost, or draw that round. Total of that gives you a score for that game. So your job is to go through the list of all of these and to compute a score each time. So let's jump into how I solved that problem. So let's see. Part 1. First of all, part 1. Does it work? Yes, it does. Okay, so the main guts of this solution is pretty simple. If we go down here, we are pretty much looping through the input file line by line. We're doing some sort of transformation on each line input. We're taking the result of that and we're making a rolling sum of it, and then we output that at the end, and that's it. So the key part is up here, which is what I've called the transformation down here. So basically what I've done is I've pretty much just manually solved this problem and then just had the computer execute that manual solution over and over again. So what I've done is I've created this hash where each input is one of the entire set of all possible inputs. So this only works here because there's only 9 different states that you can have here. Your opponent can either play rock, paper, or scissors, and you can either in response play rock, paper, or scissors, and therefore you have this really defined bound set. And then I've been able to just hand compute the scores for each one. So you'll see there's a bunch of 1s here, a bunch of 2s here, and a bunch of 3s here. That represents the constant score that you'll get if you always play a rock. Same with always play paper and always play scissors. And then we've got the wins and losses worked out here in this other part. So I just did this to make it easy for me to type it out and to think through the logic, and then also easier to explain what's going on. So 0 here for a loss, 3 for a draw, 6 for a win. And yeah, that's pretty much it. It doesn't get any more complicated than that. So this kind of like lookup table approach and static approach, it works really well here just because it's a really small set. Yeah, like there's not, the state space isn't very big, so the computation of this is quite easy. You can work it out by hand and you can then just hard code it in. And this approach kind of in real life, in practice, does work for reasonably large spaces. The key is that it's finite. So if there's always a finite amount of different states, then something like this works really, really well. If you don't know then what that like stat is, then that's where you can run into problems because you can't just map it out easily. So that's pretty much my solution for part 1. So moving on to part 2 then, I got a little bit worried about this because as I was solving this part and I wrote this whole thing up, I was suspicious that I had maybe done something silly here and that this wouldn't be able to be reused for the other parts of the problem, which we'll see now what the other part of the problem is. So for part 2, basically you're told, your elf comes back after being called away and he tells you that the assumption you made about what the puzzle input means is actually wrong and you have to do something else. So at this point I was like, oh no, maybe I have done completely wrong and I'll have to rewrite this entirely. But I found this line, which is great. It says the total score is still calculated in the same way. So it's like, aha, that's great. So it means that my code can still work because the total score calculation is still the same. I have code here that calculates total score, so that's great. But what you're told the difference actually is that XYZ don't just mean your hand signal that you guessed they meant. What they actually mean is they mean for what you're supposed to do in that game. So if it's an X, that means you're supposed to lose that game. If it's a Y, you're supposed to draw that game. And if it's a Z, you're supposed to win that game. So what you actually have to do now is you have to figure out what your move is supposed to be. So if your opponent plays a rock and you're supposed to lose that game, you need to calculate what your move is supposed to be. So once you've done that, then what you have to do is you have to calculate what the score for that output of the game is going to be based on the same rules as part 1. Okay, so let's go to my part 2 solution. So we have our same score hash up here because it's the same, hasn't changed. But we now have a new hash down here. Again, I was able to do a lookup-based approach here because I knew the state space was quite small, and I'd be able to hard code it and work it out by hand. And then the only difference for the overall solution is there's just one extra step basically in the loop. So we go through each line by line. At the start, we're going to extract what the opponent's play is. Then we're going to look up what all the possible plays are, and the output of that will tell us what we should be playing. So we have in here all the entirety of all the states. So if our opponent plays rock, what each output is supposed to be. So this is the opponent is playing rock each time, and we're trying to figure out if we win, lose, or draw, what we need to play to do that. So the encoding here, I've kept it to the same encoding as up here because we're going to directly plug these values into the first lookup to get our score so that we can calculate it. So we look up what we should play. We put the opponent's play and our play into a format that matches our first lookup, and we do the lookup and we add the score, and that's that. So this one also works. Yay. And yeah, that's it. It's pretty straightforward. So I think I got pretty lucky with this one, as in that I came up with a solution that I was a little bit shaky on. I thought it was a clever solution, but I was a little bit shaky as to whether I'd be able to reuse it or not for the second part. And then it just so happens that I was able to reuse it for the second part, but also not only was I able to reuse it for the second part, I was able to use the same kind of approach to solve the second part as well. And again, mostly this only works because it was a really simple set of, states that we could operate in. I was able to very easily work it out in my head and then just hard code it and then just use the computer to just do the grunt work of applying it over and over again. So yeah, that's day 2 in the books. Had fun with this one, thought it was good. Got a little bit lucky with it, but still think I came up with a kind of a cool approach to doing it. Yeah, so that's it for today. I hope you guys enjoyed. Kimchi and I will be back tomorrow to solve day 3. And yeah, have fun with this one, guys. Or I hope you enjoyed it. Hope you had fun if you've already done it. And yeah, I'll see you guys tomorrow.